Today we will start discussing simplex method. In the last one, you know that we have shown you conditions under which you can check whether the problem is unbounded, you can check whether there is a condition whose satisfaction would give you the optimality, that you can guarantee that the current BFS is optimal. So, we start basically with the philosophy of the simplex method, which is what we are going to build upon. Any mathematical method would have a basic philosophy not in the sense of what philosophers are telling, but philosophy is in the sense that what is the basic framework that we have to work upon, what we intend to do and how do we intend to do it, and that is exactly what we are going to concentrate on. So, what we have understood that if LP, that is this problem, minimize C of x subject to Ax equal to b and x greater than equal to 0. If this problem has a solution, then there is a vertex on the feasible polyhedron which is also a solution. So, which means that if I have the feasible region say like this, this is my feasible region C, is a convex polyhedron, then what I can do is compute the objective value at each extreme point and check which is the minimum. But if the number of extreme points is very large, which is often the case, then it is very difficult to make such computations and make a direct enumeration. So, what would we do is that we would rather try to find a clever way that if I have a current, I am on a vertex, and if I know that this vertex is not optimal, then I have to find a clever way to go from one vertex to other vertex, so that my objective value decreases, because I want to minimize the function. Now, how do we do that? So, we have to understand that every vertex corresponds to a BFS, basic feasible solution, and every basic feasible solution corresponds to a basis matrix B, which is a m cross m matrix of rank m, corresponds to some basis matrix B. Now, this is very fundamental. So, if my current BFS is not optimal, then I have to move to another BFS, move to a new BFS. So, if I call this basis matrix associated with this BFS as B and this BFS as B dash, and the objective function value when I take this BFS as ZB and this BFS as ZB dash, I should have at least this is what I intend to have. This is basically some sort of flow chart of the linear programming problem or the simplex method. That is what I intend to do in the simplex method. So, how do we achieve that? So, our goal in this talk today, which would be basically the end of this sort of simplex type approach to linear programming, because this is only a short patch up inside this larger course of convex optimization. Now, what we are going to show now is how to do this change from B to B dash. So, the whole story of simplex method lies in understanding how to make this change and what lies behind making this change. So, as we start to do this, we first start with a lemma, which is essential to our proofs of the main result. So, this lemma is a lemma from matrix theory. Now, I will not prove this lemma, but ask you to do in the homework. So, what is this lemma? So, let us consider B to be a m cross m matrix which is non singular, that is of rank m, means it is invertible. Okay. Once I have this, let u and v be column vectors. We are just making this distinction because we are using C as a row vector in this description. So, this column vectors in Rm such that V transpose B inverse u is not equal to -1. You can always choose such vectors, you can always make such choices. So, if this is the case, then so you should observe that V transpose B inverse u so this is what you have. Now, you have to understand why we are computing this inverse. This is this whole thing, this B plus this part, B plus this one, B plus UV transpose is called rank 1 update. This is called rank 1 update because UV transpose, this matrix is a rank 1 matrix. I cannot say it is a rank 1 matrix, what I can say is at most has rank 1, it can rank cannot be more than 1, it does not matter if you just take it to be a rank 1 matrix, it's without loss of generality such things can be said. So, now why I need this inversion business? The inversion business is very important because how do you find x b, say when you start, that is P inverse b. So, when you have the new one to find x b dash, so finding x b you need B inverse, which you will all anyway know. So, to find x b dash, which is corresponding to the new basis matrix B dash, you need to know B dash inverse. So, I have to find a formula which automatically computes the inverse. So, if it automatically computes the inverse, it is easier for me then rather than having this matrix B plus UV transpose and then trying to inverse by take the inverse by the usual matrix inversion formula, but rather have a simpler formula which will do this. And this thing will always get satisfied when we have linear programming problem, because you see this expression is well defined. If I call this expression as W, if this is -1 not equal to -1, so this cannot be 0. Now, this as I have just told, this is well defined. So, this formula is well defined. So, how to prove this formula? This you do in the homework. Maybe some tips can be given, but later on, not now. So, now our next step is to know how to change bases, and this is exactly what simplex method does. What do you do when you change a basis? You have a basic matrix B, then you replace one column of the matrix with some other column. So, you bring one column from the non basic part and put it in the basic matrix, and take one column from the basic matrix, put it in the non basic part. So, then you have a new matrix which is a basis matrix. Now, we have to understand when will you start changing the basis, what are the two conditions which will lead you to start changing the basis. So, number 1, you have to first find that there exists a J j element of the non-basic part, j is 1 to n and I is the basic part and the other part is the non-basic part. So, there must be a j for which this should happen, that is I am not sure whether my current BFS is optimal. Number 2, you have to be sure that the problem is not unbounded. This need not be less than equal to 0. So, two things has to be guaranteed: current BFS not optimal, that is the BFS corresponding to this basis matrix B is not optimal, plus you have to guarantee, which is the second one, the problem is not unbounded. See, this is not telling you that okay, I am guaranteeing you that the problem is not unbounded, it is telling you that okay, you have not been able to get the sufficient condition which tells you that the problem is unbounded. So, we are assuming that okay, for the time being now we have no condition which is telling me that the problem is unbounded. So, we know that the problem could be unbounded also, but the problem at the moment we know that we have no way to check whether the problem is unbounded. So, we go and proceed to the next step. So, the problem is not necessarily unbounded. So, these are the 2 points you require. So, we go from B to B dash. How do we do? So, we take a column AL of B, choose a column AL of this B and replace this column by a column AJ, where j is from j minus I and L is from I. So, this L is of course from I and this j is from j minus I. Now, once you put, instead of you swap AJ with this, you are swapping AL with AJ, then the new matrix that is formed is the basis matrix, means you swap AJ with AL and then that is exactly what you get. Now, how to know which column has to be thrown out? This is important. How do you know that which column you need to throw out? So, to know this, you do a little trick. The trick is as follows. Now, I will not go back and recollect with you what were the symbols. For example, I will use the symbol B bar now, and you possibly would know that the symbol B bar is already known to you. We have already given some symbols early in the course, and B bar is B inverse B. So, we are not going to go and repeat these symbols anymore. So, what you do is you compute this theta, so find the minimum of. So, now what is Yj? Yj will use a notation called Yj, which you already know. So, ith component of the jth column, so Yj is B inverse Aj. So, ith component of the jth column. Now, I know that this is not less than equal to 0. So, there is some I, some column, some component of this vector B inverse Aj, that vector must be strictly bigger than 0. So, there is at least one Yij which is strictly bigger than 0. Yij is the ith component of the jth column, where I is running from 1 to m. So, I goes from 1 to m. So, you just consider those i's for which this is bigger than 0 and then divide by this and take the minimum, and let. So, because there are only finite number of such things, you have one of them to be the minimum. So, theta, let that be equal to so if PL is equal to R, then it is the AL, then AL. So, let PL be equal to R. So, it is the Lth column. So, R is the corresponding column of the actual matrix, L is the corresponding position of that particular column in the basis matrix. So, you will know if I have PL is equal to R, right, then it is the rth column of the original matrix which is inside the basis matrix now, which is taken the Lth position in the basis matrix, that has to be replaced off. So, the rth column of the original A is now the Lth column of B which we throw out. Once you know this, how to do it, of course, we will tell you why this is making sense, right. Now, this is a rule, this is called the famous pivoting rule. This rule is called the pivoting rule, which is central to simplex method. This is nothing but Gaussian elimination. This is solving linear equations. But why this makes sense? Why this rule actually does what it does and achieves the aim that you want to have, that you have a b dash such that z b dash would be less than z b. In order to do that, we need to go a bit further. Let us make some diagrammatic representations of what we had been just speaking about. And so, let B, I represent the basis matrix through its column AK1, AKR is equal to AL. Okay. So, here, sorry, I made a mistake here, I just have to change this. The Lth column of the original matrix is the Rth column of the basis matrix which we throw off. So, we are replacing the Rth column of the basis matrix. Now, the Rth column basically K1, K2, Kr is the Lth column of the original matrix. Now, we make the change to the new one. So, it is AK1 and in the Rth position is now becomes the jth column of the original matrix takes up the Rth position of the basis matrix. So, I am changing one particular position of the basis matrix with some other column from the original matrix. Similarly, if you have done this change, you can done the corresponding changes. You have CB so, this is the m number of columns we are bothered about, because it is m cross m matrix. So, this is changed to CB dash, which is exactly this, right. So, the index set I of the basis matrix will now change into this form. It was like this, this changed to I dash, which is everything but changing the Rth number with L. Here is J. So, the Rth position has been changed. If you look at it, you can replace I dash is what? I dash is nothing but you had the I from which you have taken off L basically, and you have added up j. Is one way of looking at it, not though technically it is not very fine, because I am replacing I with k1, k2, km. Okay, just not bother about it. So, let me define this matrix, sorry, a vector, a column vector, but I am writing it as a row. So, I am putting the transpose, which is 0 everywhere except the rth position, which has the component value 1. So, this one will help us a lot when we do the change. Now, I want to define b dash. Let me see how can I put in this change that I have done from b to b dash, how can I mathematically represent. So, how to mathematically represent the change from b to b dash. To emphasize this change, I am taking the red color of the pen. Now, I am writing b dash is b plus aj minus al So, this is a matrix also. Now, if I look at it, let me take a simple case for 3 variable. It is a say a 4 by 3 matrix. Say if I take m cross n, sorry, not 4 by 3, a 3 cross 4 matrix. Okay. So, then how does b dash would look like? So, b is nothing but say A11, A12, A13, A14, A41, A42, sorry, 3 is a 3 cross 4 matrix. No, sorry, this is A, I am writing A. So, A is a m cross n matrix, this is my A. Now, suppose my B has to be a 3 cross 3 matrix. Suppose my B is this, the first 3. This is my B, right, which is the m cross m matrix. Now, this is my K1, this is my K2 and this is my K3. So, K1 is 1, K2 is 2, K3 is 3. Suppose I am replacing K2, that is A2 with A4. So, my B dash would be B, which is A11, A12, A13, A21, A22, A23, A31, A32, A33 plus A4 minus A2, right. What is A4 minus A2? A4 minus A2 is A14 minus A12, A24 minus A22, A34 minus A32, right. This is what is, this is a column vector, this is multiplied with this row vector whose rth position, here the rth position is K2, 2 is the R. So, it will have 0, 1 and 0. Now, I am doing the multiplication which I will carry out here, because I need everything to be in one page for you to. So, if I carry out this matrix multiplication, what will I have? So, it will be B dash is B, which is A11, A12, A13, A21, A22, A23, A31, A32, A33. So, you see this is a rank 1 updating formula, if you remember, this is a rank 1 update. So, now if I do this matrix multiplication, I will have what? I will have a matrix, this is of rank, this is of 3 cross 1 and this is 1 cross 3. So, you will have a 3 cross 3 matrix, which is what we require. So, what would be that 3 cross 3 matrix? So, you take this one, multiply with this, multiply with this, multiply with this. So, it will be A, so it will be 0, A14 minus A12 and 0. Then you will multiply with this, so it will be 0, A24 minus A22, 0. And then you will be multiplying this with, this will multiply with this, all of this. So, A34 minus A32, 0. Now, if I add these two matrices, see from here I have gone up here, right. So, now if I add these two matrices, what you will get? When you come here, you see this all cancel with this, and so this will give me A11, A21, A31, A14, A24, A34, A13, A23, A33, and then as the friend says, voila, this is exactly what is required. This is exactly what I wanted, change the second column by the fourth column, and that is done by using this rank 1 update. But if this is my new basis matrix, I have to know how to find its inverse, which we will know from the rank 1 update formula which we have just presented, and also now we have to show that the ZB that you get here, ZB dash, is actually having a lower function value than what you have with ZB. Now, let us compute the B dash inverse, which is required to compute ZB and all those things, XB dash. Now, I will keep on writing with the red pen to emphasize how important this part is. So, now we have to compute the rank 1 update. So, to compute the rank 1 update, I have to first show this quantity is not equal to minus 1, or this is strictly bigger than 0. So, let me, this is to show. So, how do I compute this? So, I will just again write. So, it is 1 plus UR transpose B inverse AJ minus UR transpose B inverse AL. Now, what is B inverse AL? What is B inverse AL? That is something you need to understand. AL is the thing that you are replacing. AL is actually, if you look at it, AL is the column that you are replacing. Now, if you look at the basis matrix, AL is one of the column, is the rth position in the basis matrix. Now, if you do B inverse B, you get identity, the identity matrix B inverse B, which you know very well. Now, what would happen if I operate the inverse B inverse on the rth column of B? It will give me the rth column of the identity matrix, which is nothing but UR in this case. So, this is equal to 1 plus UR transpose B inverse AJ. But this is just one. So, I will cancel these two to get. So, what is B inverse AJ? B inverse AJ is Yj by definition. We have already mentioned many times that B inverse AJ is symbolized as Yj. Now, what is this? This is YRJ, the rth component of the jth column of B inverse AJ, this vector, rth component. But by the pivoting formula which we have got, by the pivoting that we have done here, this pivoting tells me that this damn thing is strictly bigger than 0, and hence we have proved what we wanted. Now, we use the updating formula to compute the B inverse, sorry B dash inverse, which by the updating formula is B inverse minus this is exactly the formula, right. Now, this with this formula I can conclude, which you might be asking suddenly what is happening, but sometimes you need to work things out to have the actual fun of the subject. So, this to this is your homework, because YRJ is strictly bigger than 0, then this is a well defined, as we have seen. So, this is a well defined thing. So, this is exactly the formula. Now, I can now write xb dash. Xb dash is B dash inverse B. So, B dash inverse B you can again compute out to be this, and x k is equal to 0 for k which is in J, but not in I dash. Now, how do you come is again homework, which will be part of your homework assignments that will be given at the end of the course. This will be, though I am mentioning them as homework, this will also come in a nice form at the end of the course. So, you can try them out, and you will have my email address at the end. If you are having a problem, you can just let me know and I can send you the details. Now, once you know that is xb dash, you can prove that xb dash is also bigger than 0. If you go here, from here you have to prove that xb dash is also bigger than 0. Now, how do you prove that xb dash is bigger than 0 would be your concern. Of course, B inverse B is bigger than equal to 0, you have to prove that this is actually negative. So, this theta is positive. So, you have to prove that this is negative to prove that this is bigger than 0. So, your job is to show that this is bigger than 0. Is also homework. So, I have given you quite a bit of homework. This is a very important thing, that is why you need to compute out this, because while you compute out this you have a lot of understanding of the mechanism of simplex method, and that every student needs to do it himself. Now, you compute. So, once you know this, you know that x b dash is feasible and it is a BFS by your definition. Now, you write down z b dash is C x dash, but by definition, by our notations, it is this. Now, what is C b? C b dash, it is nothing but the same formula for the B, C j minus C L, this into B inverse B minus theta B inverse A j minus U r. Now, you will compute to find the following. So, you will be able to write the whole thing as, because this into this is Z b. So, you can write the whole thing finally as if you look at this whole thing, here this jth row, the jth row which is entering the scenario, entering the basis, that has a pivotal role to play, because we are computing B inverse y j, B inverse A j is equal to y j using that particular row A j, that particular column A j of the matrix A, and then we are computing the y r j. So, this is very important. The theta is very important, because this theta is computed only when you know j, and j is known because you have a particular j for which you have those two conditions, that the sufficiency condition for optimality is not valid, sufficiency condition for unboundedness is not valid. If you have that particular jth column, then you use that to do the pivoting, and you know that which, then that is the column that will enter the basis, that you are sure, but knowing which will enter the basis matrix, you use that to find which will get out of the basis matrix, and this fact is actually working, because it is giving you the new matrix, and now we will show that we can show that the objective value decreases. So, this thing you know has been strictly less than 0 in the beginning. So, this is the j that we have been working with, and see this theta is positive. So, this whole thing is, because it is strictly less than 0 and theta is greater than equal to 0, this is less than equal to z b, and that is what we wanted. See, observe that our first starting has been with this. So, I am giving you a j where this is satisfied, these two conditions, and with that j you start working with that particular j, because you know this, you know that there is something like this, and then you compute the theta. Once you compute the theta, you get one particular component r, and corresponding to that r has to be one among the m components. So, that corresponding component is the particular position in the basis matrix, particular column position in the basis matrix which has to be thrown off, and this A j has to be put in. That is if it is r is equal to P L, then you are throwing off the ALth column of the matrix which is in the rth position of the basis matrix. So, it is that j, that starting j that we have, we are working with that j throughout. So, that is, so we have told you how to make the update from B to B dash, what is this inversion formula, and actually we have basically computed x b dash. So, this theta is a pivotal role, because at the end I am not really bothered with B or B dash, at the end I am only bothered with what? I am only bothered with x b and x b dash. If I know x b given to me in the beginning, starting basis matrix, that is why we always take the starting basis matrix to identity, that is what we do in the standard implementation of the algorithm. which we will not talk about here. There are many, there is a separate course here which talks about how to implement the algorithm, and we have shown that how can we earlier that we can introduce slack variables and get a basis matrix. So, if I have a starting basis matrix B, if I know that basis matrix, at every step I can just compute the theta. So, this theta once I have computed, I will immediately know x b dash. So, but it is very important to know b dash inverse also, because these b dash inverse would be used to go say for b double dash inverse or b x b double dash. So, if you go from b dash to b double dash, these b dash would become very important, and as a result of which these two steps are very important. Okay. So, you have basically done the simplex method now, and we show that okay, our approach actually solves this. Now, what we are going to do is now to write down the simplex method in a more formal way. This is given from Manfred Padberg's version from his book. Go back to the black one. So, what is step 0 is to initialize everything. Find a feasible basis. Its index at I, that is you have to know what are the columns which are inside the basis matrix, and initialize Pk for all k in I. So, basically you know which Pk is the which original column of the original matrix say is now in the basis matrix. If none exists and no basis feasible basis exists, feasible basis matrix, I should write feasible basis matrix if you want to be more erudite. Then stop, LP is infeasible. There is no feasible basis matrix, so there is no infeasibility of the problem itself. Else, if you can find compute B inverse and B bar equal to B inverse B, okay, and initialize CB, which corresponds to this B, and you know what it means. Step 1, compute C bar. Of course, A is given into two parts, B and N. It is the N part which is important, but does not matter. You can just do this computation. If C bar is greater than or equal to 0, then set x b equal to B bar and x n part or the remainder part, whatever, whichever sign you want to give, the non basic part to be 0, and this is the optimal, that is x equal to x b 0 is optimal. Else, if this does not happen, choose j element of all k which belongs to j minus I, but for which C bar k is strictly less. So, choose one j, basically you choose that value of j for which among all the k's C bar k is of the least value. So, that you choose as j. So, everywhere you have to put an end of the loop, which I should be putting. So, here also I should put this is if none exists, then this end loop has to end if the if loop ends. Here if this happens or else choose j and end the loop. Step 2, compute. This is also very important to know. You have chosen the j, what is this? No, if, so it is all if then loop, if then else loop basically, then stop, LP is unbounded. This is already we have proved. Else, sorry, if this does not happen, then compute theta, which is mean of, you know how to do it. So, this is exactly what we have just learned. Choose the lth position in I such that B bar PL, that is PR is L basically in our case. R is PL, so KR is equal to PL. So, PL is that Lth position, PL is L, and PKR is R. So, set R is equal to PL. So, this is the, so the from the rth position, the vector in the rth position AR, AL would actually get out. That is exactly what we have done, nothing else. So, again we end the if loop. So, you could even think of writing a program on this. So, now the iterations, the updating, step 3, now set is B dash, sorry, B is now assigned to, I cannot write it in that format, I am writing in a computer programming format. So, CB, so this is assigned to basically, you can also give an arrow like this, does not matter. Compute P inverse B and go to, so with the new B you compute B inverse B and go to step 1 and do the same checking all over and again. So, can you write a computer program with this? That is very important. Can you, or can you write a program? That will be fun to do this. So, today we went the simplex method, and in the next class we are going to speak about a very exciting topic called interior point methods in linear programming. This whole idea of linear interior point methods, which gave polynomial time algorithms, actually revolutionized the field of convex optimization. And so, what we are going to do from the next class is a very, very interesting and some sort of a revolutionary topic in optimization theory. Thank you very much.